Hello. In this lesson, we look at another brute force algorithm for sorting called bubble sort. We have already seen selection sort as one of the simplest algorithms for sorting. Bubble sort is also a simple algorithm. The idea in bubble sort is slightly different from the one in selection sort. In selection sort, we always pick the smallest or the minimum element and we put it in its proper place. Once and for all, that smallest element would move to its final position in the array. In bubble sort, we do things slightly differently. Here, we locally do the sorting. We see any two numbers that are out of order and we exchange them. So we gradually improve the order of all the elements, and the numbers in a way bubble up to their final positions. Just like a bubble rises in water to the surface, each number bubbles up or rises to its correct position in the array. So stated simply, the idea of bubble sort, to sort n numbers, let's say in increasing order, is to look at every pair of consecutive numbers. If they are not in increasing order, if they are out of order, we exchange them. Right? If the two numbers are in decreasing order, we exchange or swap them. And we continue doing this until all the elements are sorted. Right? In bubble sort, after I steps, the last I numbers will be sorted. In selection sort, the first I numbers were sorted. Here the last I numbers are sorted. So what happens is the largest element bubbles up to the last position in the array. Then the second largest element bubbles up to the second last position in the array, and so on. So just like in the case of selection sort, let us first look at an animation to visually see and understand how bubble sort works. So here is an array of 8 elements. So first we compare 6 and 5. They were not in increasing order, so we exchange them. Now we are comparing 6 and 3. They are not in increasing order, so we exchange them. Now we compare 6 and 1, exchange them again. Right? Keep doing this. When we compare 6 and 8, they are already in increasing order, so we don't do anything. 8 and 7, we exchange because they were out of order. Right? So after one loop of this, the largest element, which in this case is 8, bubbles up to the end of the array. Right? So let's observe what happens to the number 7 in the next loop, in the next iteration. Right? The number 7 is currently here. It should bubble up to this position at the end of the second loop. Let's see if that happens. Right? So now we exchange 5 and 1. 5 and 6 are already sorted. 6 and 7 are already sorted. Right? But 7 and 2 are out of order. Right? So 7 is going to bubble up to this position now. Next, when we compare 7 and 4, 7 is going to bubble up to its final position. Right? So similarly, in the next iteration, in the next loop, which number should bubble up? The next highest number 6 should bubble up to this position. Right? Its correct position. Let's see if that happens. 1, 3, 5, 6, they're all already sorted. 6 and 2 are not sorted, so 6 bubbles up to the next position. 6 and 4 are not sorted, so 6 bubbles up to this position. So after these 3 rounds, the last 3 elements of the array are already sorted. The remaining 5 still need to be sorted. So this is how bubble sort continues to pick the largest element and bubble it along the way. But while doing so, it will have already sorted some of the remaining elements as well, because wherever we notice elements being out of order, we exchange them. Right? So this goes on, and in the end, all the elements will be sorted. So in this case, actually after this swap, all the elements are already sorted. But being a brute force algorithm, bubble sort doesn't know that the elements are already sorted. So it will continue to check the remaining ones. So these are wasted comparisons because this is not an intelligent algorithm. It's a brute force algorithm. Right? Now finally all the elements are sorted. Let's look at one more animation which is really visually very effective. Here is a set of points. See how they kind of fall into place. They are all bubbling down in this case to fall into their correct positions in the array. So what is happening here is the x-axis is the index of the array element, and the y-coordinate of each data point is its value, the number, the value that we are sorting. So in a sense, you can think of these as vertical lines, except the lines are not drawn, only the tips of the vertical lines are shown as dots. So as bubble sort progresses, the elements kind of locally get sorted. That idea of local sorting is clearly visible in this particular example. And the array is getting sorted from the right to the left, right? So the highest element, the dot with the largest y coordinate, gets put in its proper place first. And the elements with the smallest y coordinates bubble down to their correct positions towards the end of the operation, right? So bubble sort locally arranges elements so that they all fall into place. So you can see that in a sense the total width of the scatter of the elements is decreasing as bubble sort progresses. They're all getting compressed onto that curve, that line which denotes the final sorted array. That's because any local imperfections we keep correcting until every element falls into its correct position. So this is bubble sort. Now let's see if we can write an algorithm for bubble sort. In English, bubble sort takes an array A of n elements from 0 to n minus 1, and the bubble sort algorithm is rather simple. From beginning till the end, you do another inner loop where from beginning till the end of the unsorted part, swap consecutive elements if they are not in proper order. That is, if any two consecutive elements are in decreasing order, exchange them so that locally now they are sorted, locally they are in increasing order. Keep doing this until all the elements are sorted. Right? Let's add more detail to make it a proper pseudocode algorithm. So bubble sort takes an array of n elements 0 to n minus 1. We loop from I equals 0 to n minus 2, and in the inner loop we loop again from 0 till the unsorted part. After I loops, the last I elements are sorted. So we ignore the last I elements, n minus 2 minus I. Right? And what do we do? If any two elements, aj plus 1 and aj, if they are not in increasing order, that is, if aj plus 1 is less than aj, if it is greater than or if it is equal to, we don't touch it. If it is less than aj, then we exchange them. Swap aj and aj plus 1. This is it. This is the bubble sort algorithm. Let's take an example and see how it works. So let's say the array is 43, 9, 26, 4 and 15. These 5 elements are to be sorted. So I will start with I equals 0, j equals 0. Both of them will be pointing to the number 43. Is aj plus 1 less than aj? Yes, these two numbers are in decreasing order. So we exchange them. So the new thing will be 9, 43, 26, 4, 15. Right? Next we compare 43 and 26. Are they out of order? Yes. So we exchange them. Right? We exchange them. We get 9, 26, 43, 4, 15. Next we compare 43 and 4. They're again out of order. Right? So we get now 4, 43 and 15. Finally we compare 43 and 15 and we get 9, 26, 4, 15, 43. So what happened? You can see that 43 kept moving to the right or bubbled up to its correct position in the array. It was the largest element and it happened to be in the first place in this example, so it kept bubbling up till its final position. Now we don't touch this anymore, right? This element is already sorted, we don't touch it. We continue with the remaining elements. 9 and 26 are in the correct order, 26 and 4 are out of order. So we get 9, 4, 26, 15. I will not write the already sorted part, right? Now you will notice that the rest of the array is not sorted. For example, 9 and 4 are out of order, but we will come back and look at it later. We are not going to exchange that right now. Next, what will happen? We have to compare. So we compared 9 and 26 and 4 and we exchanged them. Now we have to compare 26 and 15. So we will get 9, 4, 15, 26. So at this point 26 is its correct position. It is sorted. We continue with these two. So we end up exchanging 9 and 4. We get 9, 4, 15, 26 and then 43. So at this point the array is sorted, but bubble sort doesn't know that. It will continue to compare the remaining elements and it will not find anything out of order. So there will be no more swaps and the array gets sorted. So each time the largest among the remaining elements is guaranteed to bubble up to its correct position. The remaining elements, the unsorted ones, may or may not be in their correct positions. That we will only know at the end of each loop, at the end of all the loops, right? So this is how bubble sort works. In the outer loop, we repeat the operations n-1 times, right? This is done n-1 times. In the inner loop, the number of comparisons we make keeps decreasing because we are only going up to n-2 minus I, right? And each time, if anything is out of order, we swap those two elements. This is how bubble sort works. So how do we analyze the complexity of bubble sort? How long does it take? How many operations does it do? How many times does it do the swap? Right? This is not easy to answer because it does a swap only when two consecutive elements are not in correct sorted order. They must be in decreasing order and we are trying to sort in increasing order. Only then a swap occurs. So how do we know how many times this occurs? We don't really know. This depends on the nature of the input. If the input is already sorted, then no swap may occur. If the input is not sorted in some places, then swaps will occur in those places, right? So there is no way to know exactly how many times swaps occur for an arbitrary input. So let's instead look at how many times comparisons occur, right? So in the outer loop, we go from I equals 0 to n-2. In the inner loop, we go from j equals 0 to n-2 minus I. What do we do each time? We do one comparison. We compare aj and aj plus 1, right? So if you sum this up, what do you get? Right? So this is nothing but sigma I equals 0 to n-2. If I now compute the inner thing, right? What is that? So this is like n-2 minus I plus 1, right? Or in other words, it is nothing but sigma I equals 0 to n-2 of n-1 minus I. So when I is 0, this is n-1. When I is 1, this is n-2 and so on. When I is n-2, right, this is 1. Right? And so like this you get this summation, and if I add them up, this is the same thing that we saw in the case of selection sort, namely n into n-1 by 2. So this bubble sort complexity is also O(n) squared. The most significant term here is of order n squared. So to sort n elements, bubble sort does O(n) squared number of comparisons. The number of swaps changes. It depends on how well sorted the input data was. In the worst case, the number of swaps will be high. In the best case, the number of swaps will be low. In the average case, the number of swaps will be somewhere in between. But the number of comparisons is always the same. It's always O(n) squared. In fact, it is theta n square, because it does not depend on best case or worst case or average case. The number of comparisons is always of the order of n square. So we can say that bubble sort is also of complexity theta n square. So here is a question for you. The best case and worst case inputs for bubble sort are respectively. That means, is it reverse sorted and already sorted? That is reverse sorted the best case and already sorted the worst case? Or option B, is already sorted the best case and reverse sorted the worst case? Or both already sorted is the best and worst cases? Or both reverse sorted is the best and worst cases? What is the right answer? Well, the right answer is B. If the input is already sorted, that is the best case because the number of swaps will be low. The number of comparisons will still be the same. If it is reverse sorted, that is the worst case because maximum number of swaps will happen. But the number of comparisons will be the same for both. That is bubble sort for you. Thank you.